Hello everyone, welcome back to the another session in design and analysis of algorithms. The topic name is compressed tries. This topic you will find in 4th unit 7th topic. Prior to this video, there is other video which is standard tries. So part of the standard tries, we come to know about tries is one of the data structure and which looks like exactly a tree structure, but these tries are different from the trees. Tree can store numerical values, but the tries what we have is to store alphabetical characters. That was the difference, and there are many differences. So while you are going to learn about the content of this video, you will come to know what exactly the differentiations in between trees of data structures and tries of data structures. Both are the concepts of data structure only, but the major difference is what the trees what we already come across with data structures are to store numerical values. The tries what we are going to learn is to store alphabetical orders or alphabetical characters. Now, so this video is to explain about compressed tries. The name itself it says that we are going to compress the try to reduce the searching operation time. Now let's see how it will be. Now all the searching trees are used to store the collection of numerical values, but they are not suitable for storing the collection of words or strings. So this try will store the data in the form of words or strings. So whatever string you have, that you can keep into your tree structure, whereas this cannot be done with the existing data structures what we have. Now try is a data structure. As I said, now try is a data structure, and the uniqueness of this try is what it can store the collection of strings and make searching of a pattern in words more easy. So the term try came from the word retrieval. So there are some properties, and these properties are of the try for a set of strings. So those properties are the root node of the try always represents the null node. So when you construct a try, this root node should not be filled up with any alphabet. That means no alphabet is to store in this root place. So root always will be null node. From root node we'll extract all other nodes to store your data. And the second is each child node is sorted alphabetically. Let's see that if I wanted to store two strings in the try, that means the one string is some bull, the other string is one stop. So you cannot place stop prior to this bull. You will first of all construct the node to store this bull, and later you will construct the stop. That means the child nodes of this root node will be formed in the tree or will get generated in the tree in a sorted fashion, and each node can have a maximum of 26 children. As I told you that we'll store alphabetical order, or else we'll store only words. Words can frame with only 26 alphabets, such that maximum a node can have 26 children. So each node can store one letter of the alphabet except the root node as far as standard try is concerned. So in the prior to this video, I advise you people to watch the standard try. So in that standard try, you might have already come across the tree structure, how it will be. So there you noticed this, that each node can store only one letter or one alphabet except the root node. Now we'll talk about the compressed try. So compressed try, basically it is derived from the standard try. So that's the reason I'm taking this example and I'm constructing the standard try first of all. So standard try is what will construct a try where each node will be constructed with the single alphabet. If you check the entire tree, there is no node with two or more alphabets. All the nodes are created with the single alphabet. Okay, now so let's see, there is an example so which I took from the textbook. So this normal example is what there are collection of words what I wanted to place in the try. Now how I can place these? So I told you beginning of this slide that all these things has to be placed in the alphabetical order. Though I have here cat first place in the order of the strings. Now let's say that our set of strings. The first string is what? Cat. So I'm not going to place cat in the first place. Now this is my root node. So I'm storing here first of all B. B is what? To store bat. Okay. Now let's see how I can place this bat. So first of all I'm storing this B, and later I will be storing A and some T, bat. Fine. So after I place this bat, there is the other one which is ball. In ball already B and A are existed in the nodes. Now I'll make use these two nodes to construct the L and L, ball. Okay. Now so with this you got two words in the try. One is BAT bat, the other one is BALL ball. So generally if you see the word of bat or ball, now you will be starting with this node to the leaf node. So now your L is leaf. Okay. Now this T is also leaf. To make understand, I'm just giving this dollar symbol to represent this is the end of the string. If there will be nothing happen if you are not placing dollar at the end of the string, it can leave as it is also, but only for the clarification that the string is ended up, I'm just giving dollar symbol. This dollar will ensure you that it is the empty string, end of the string. Dollar will ensure you that it is the end of the string. So now I done with ball and I done with bat. So it is end of the string, end of the string. Now let's see. If I have any other word with starting with B. So bat is done, ball is done. Is there any other word with B? Yes, BE. Let's construct. Already B is a node in the try. So I can reuse this B to form BE. So I'm just creating a node with the E alphabet. So BAL ball has done, BAT bat completed, BE completed. Now just keep all these dollars to ensure that it is the end of the string. So B part is done. So B is a subtree, done. Now find out the other alphabet. Is there any in the set of strings? The other word is what? Cap and cat. It will start with C. Now let's construct it. Now let's see here, before you construct the node, there are common alphabets in both the words cat and cap. What are common? CA common in cap, CA common in cat. Now CA will be the common nodes for cap and cat. So as I finished cap and cat, I'm just giving dollar symbol. Okay. Now the other word is rat. So I'm just giving rat. So this is the way how I have to construct the rat. Now what is the length of the string here? The length of the string always will be calculated from the node to the leaf node. So this is what a particular string what can be placed in try. Now what we are going to see is how I can generate compressed tree from the standard try. Now let's see. So before I go to that, let's understand the time complexity of this. A try searches a string in big O of m time complexity. This m is nothing but the length of the string. So the length of the string, whatever. Let's see. If I have 5 characters in a string, now I wanted to search bridge. Now it is what? 6 length. That means the number of characters is equal to the length of the string. How many characters I have? 6 characters I have. So to search this string, how many nodes I have to visit? Obviously 6 nodes I have to visit, because B will be placed in one node, R will be placed in other node, I will be placed in other node. So I have to visit all these nodes and I have to require this much of time complexity. So the time complexity to search one string in standard try is what? Big O of m. That is what? The length of the string. Now let's understand about compressed try. So the name itself, it tells that we are going to compress it. Now it has the following properties. It is an advanced version of standard try. Each nodes, expect the leaf nodes have at least 2 children. It is used to achieve space optimization. That's what. So we'll reduce the length of the string. Let's we see how we will reduce the length of the string in compressed trie. We'll see with an example. And the compressed trie derives from the standard trie. Now I'm giving the other example. So in this example, there are some couple of words: bean, bell, big, bull, stock, stop. These are what different words. Now I'm going to construct a string, a compressed trie. Before compressed trie construction, we have to construct standard trie, because standard trie derives always from compressed trie generates from or derives from standard trie. So this is what standard trie and this is what compressed trie. Now let's see this one, that now we'll take the example. As I told, the example is what? Now I'll take some example. Now the example is some S is equal to, the words are bean, big and bell, bull, stock, stop. Now let's see how we will construct the compressed trie. So before you construct the compressed trie, you have to construct the standard trie. Now how I can construct the standard trie? Now it is the root node. As we know, root node should not place any of the character or any of the alphabet. Now let's begin that. From the root node, what are the letters you have? Bean, big, bell, bull, stock, stop. What is the first alphabetical letter? Before S comes, there will be a B, right? So now I'm constructing B. So what words are there will start with B in the given set of words? Bean, big, bell, bull. Correct? Now I'm placing here bean. B, A and N. So to place your big, before big comes bell. Correct? Now what we'll do is, we will be placing, already to place your bell, already BE is there. So you cannot place BE again. Bean has done. The next is what? Bell, I have to do it. So already BE was there in the trie. So now I'll reuse this and I construct only L and L. So with this, bell is also finished. Now the next is what? Big. So in big, the first alphabet is B. That already here B node is there. So I'm just taking I and G. Big. Okay. Now the next is what? Bull. So B is only the common alphabet. So let it be the B. And here it is B, U, L and L. Fine. Now the other one is what? Stock. So stock is the other alphabet. So I have to take S here and T here, O here, C and K. So here in the stop, STO already there. STO is already there. Now let's construct the P under here O. Now, so this is the way how we'll construct the standard trie. Now let's see how I can do the compressed trie. So before you go for compressed trie, let's know the steps to make the compressed trie. Here, whichever are in single path, that only can be compressed. So single path is where, let's see from the root, always root should be empty. So now root is having 2, so you cannot combine these two. Again, B is having 3 children, you cannot combine this. So E is having 2 children, you cannot combine this. Now you can see this one, A is having only 1 children. Now you can combine this AN. I'll figure it out with the other ink. AN you can combine. Now LL can also be combined. Why I am combining only AN? Because A is having no other children. That's what I can combine AN. So there won't be any difference if I write AN as one word or like this. So what I'll do is, I'll make this one word which is AN. I'll make this one word which is LL, and IG also the one word IG. And here also from the U, this is all single notes. I can club entire this one. Now, in the case of this, CK can be combined, compressed, and P. Now, and STO also can be compressed. So, the basic use of this is what? When a node is having 2 or 3 children, you cannot combine, you cannot compress that with any node of the value. So, with this you can generate the compressor trie. Okay, now, so in any trie, each and every path from root node to leaf node indicates a string. So, though you compress it or though you combine this AN, this AEAN is one string. So the main advantage of the set of string is storing the set of strings. Now we will construct compressed trie from the standard trie. Compressed trie is, instead of constructing a node of each letter, if we can compress some of the nodes automatically, tree height is reduced. Searching process also get minimizes. Now let's see how compressed trie. Now this is what the standard trie and this is what the compressed trie. So that AN has been combined, LL, IG, ULL, STO, CK. These are what combined words. Now you can read the same way, that BEAN, bean, BELL, bell, BIG, big, BULL, bull, stalk, stop. So the meaning will not get changed, but the height of the tree will get reduced. Now this time searching operation will take less amount of time. So now we'll see the memory representation, how it goes for compressed trie. So whatever strings we have, that will give with the index numbers. That means now we'll see the memory representation. So the memory representation is what? S of 0. That means set of strings, no, these all. So we'll be giving the index, 0th index, 1 index, 2 index, 3 index, 4 index, 5 index. Now S of 0 is having bean. Now S of 1 is what? BELL, bell. S of 2 is BIG, big. Now S of 3 is BULL, bull. S of 4 is STCK, stock. S of 5 is STOP, stop. So here, so this is at 0th index, first, 2, 3, and all are having maximum is 3rd index, but only STOCK is having 5 alphabets in the word. So I'm just giving here 4. Okay, so this is what the memory representation of your compressed trie. With the memory representation, we just construct the compressed trie. Now let's see how I can generate the compressed trie. Root node is always empty in the all the tries, whether it is standard or compressed or suffix. In all the tries, root node will be empty. Now, so here what is the first alphabet? It is what? B, right? So B is in which index? S of 0 index. So I'm just writing here 0, comma. I'll write 3 things here. The one is IJK. I'm indicating with the. So I'm going to store each word in this way, that I indicates the index of the string, whether it is S of 0, S of 1, S of 2. So I is pointing the index of the string and J will be the starting of the word, K is the ending of the word. So as I have only one word, one letter in the word, I am just giving all zeros. Okay, that means it is only B. B is belongs to S of 0 index, and B word letter has started in the 0th index and it is ended to 0 only. Now, so the next is what? E. So this is what actually B alphabet. It is E alphabet. E has started where? E also belongs to S of 0. Now it is 0th index, and J is what? Starting of this. So where it is started? In the 1 index. So I am just pointing 1, where it is only one letter. So it ends only 1. Now the next is what? AN. The third is what? AN. So AN is the word. So A is the beginning one, A is the beginning, N is the ending. So these two words or these two characters or this word is belongs to S of 0 index. Now S of 0, right? So point here 0th index. Now A has started in which index? A has started in second index and it is ended. AN is a word. A beginning is 2, ending is 3. Now it is 2, 3. Okay. Now, so B in memory representation has done. Now let's see about LL, bell. So where LL will get placed? So LL also what? It's belong to 1 index, bell 1 index. So 1 comma. L has started at what? L has started in the second and L is ended in the third. So 1, 2, 3, bell has done. And the next, big. So IG, big. So in the big, IG, big is belongs to 2 index. Now let's write first of all it is 2. I started at what place? I started at 1 index, G and 2 index. It is ended in the G. So the place of G is what? 2. So I wrote it. Now it is the third is what? Bull. Bull is belongs to third index. Now write down 3 and it is what? ULL. Now let's write first of all ULL. U started it with position U 2. Now 2 U started at 1. It is 1, right? Because we started with 0, 0, 1. So 1 comma LL. So that is 2. 3 1 3 ULL 3 1 3. Now the next is what? STO. So now STO is what? S is at stock is in the 4th index. Now S has started in 0th and ended in 2. Now CK. This is what? CK and this is what? P. So CK is what? 4th string, 3rd place, 4th place. Now let's see. CK, stock word is belongs to 4th index and CK is what? C started in 3rd position, K ended in 4th position and P is what? P index is what? 5 3 3. 5 is the place of the string, the word. P is belongs to stop word and it is available in the 5th index and P is the character which started in the 3rd place and which ends in the 3rd place. So this is what the memory organization of compressed trie. Thank you all.